In this lesson, we'll learn non-parametric methods to analyze data. In particular, we're going to learn how to do one-sample test, two-sample comparisons, and analysis of variance when the data do not follow normal distribution. What we will cover in this lesson include the Wilcoxon signed rank test, the Wilcoxon rank sum test, and also Kruskal Wallis test. These three tests are all rank-based methods. Because of rank is used, it removed the parametric distribution assumed for the data. First, let's talk about the one-sample method. In past lessons, when we learned the comparison of a single population parameter to a given value, for example, the mean equals to 0 or the mean is equal to another given value, we are all assuming that the distribution follows normal. And even if we do not have such a normal distribution, we have to have sample size is large. Beyond that, we also required that the data has to be continuous variable numerical value and they are independently observed. Unfortunately, the real world often have data that are categorical, or they could be, for example, just the integer value rather than a continuous variable having normal distribution. So this lesson, we are going to learn a method to handle the data that's not necessarily normally distributed. In the Wilcoxon signed rank test, it will combine both the rank and the sign of the value, the comparison of this observed data with a given value. So the setting for the Wilcoxon signed rank test is here, described here. There are two possible settings. One of them is that we have a single sample observed from a population, and this population distribution may not be normal. It could be arbitrary distribution. And we want to see whether the median of the data of that population is equal to a given value. Let's say the value we are interested is theta 0, and the median is theta. We want to know whether the theta and theta 0 is equal, or either theta greater than theta 0 or theta not equal to theta 0. So that's one sample setting. We simply look at whether the median is equal to a given value or not. Another setting is the two sample case. In this setting, we have two repeated, we have two samples observed, but these two are actually related in the sense that each subject is measured repeatedly twice. One, for example, before treatment, and one is after treatment, and that's measured on the same subject. In that case, we have paired data. And in the paired data, we could consider the difference between the observed before and after treatment, and then that difference becomes one single sample, and when we try to test whether the median of the difference is equal to a given value or not. After we take the difference and we check the median of the difference equal to a given value or not, essentially we're trying to compare the median of the two samples, the two paired samples, to see that median difference of those two paired samples is equal to a given value or not. In the Wilcoxon signed rank test, we'll try to consider how is each of the value differ from the median. And this value differ in the sense that we look at both the sign, whether it's less than the median or it's greater than the median. And in addition, we also try to see how big is the difference. The basic assumptions for this test to be valid is that the data are, let's say, we are either having a one population or have a difference of paired sample. Okay, so here my notation is simply x1 through xn. That's the observed data or the difference between the paired samples. And the assumption is saying that x1 through xn is a continuous symmetric about the common median theta. Here we say it's continuous. In fact, it's not necessary to be continuous, but when it's continuous, we will have less of trouble. For example, the data will not be tied. Since when we learn about a continuous distribution, we know that the probability of tied of a single observation is always an observation equal to a single value is always 0 because of a continuous distribution. Therefore, when we look at two values being identical for a continuous random variable, that is 0. So here, this is just for explaining how the test is constructed, but it's not necessary to have continuous distribution. Instead, we could consider the data that are, as long as the ranking makes sense, is meaningful. Okay. So that's one thing. The next thing is we need to test. What we are going to test is this median equal to the given value theta 0, or the median is not equal to the given theta 0. So that's our test. For the Wilcoxon signed rank test, here are the steps of how do we conduct the test. We'll first try to look at each of the observed value compared to the median. So basically, imagine the test. We have data symmetrically around the theta 0, and we would like to consider how is this xi different from the theta 0. If xi is bigger than the theta 0, then you will have the value observed to the right-hand side. Say here is our theta 0, and you have some observed values on the left side and some values on the right-hand side. This di simply measures how big is the deviation of the observed value from that theta 0. So it's deviation, and then we consider just the distance. So take the absolute value that measures this distance. Then afterward, we will try to get the rank of all these distances. So if, for example, suppose theta 0 is here, and what we have are only 3 observations. In this case, this is the theta 0, and this is the D1 absolute value, and this part from here to here, this is the distance of the D2 absolute value. And at this point, if we consider the distance this much, that's the D3 distance. Out of these 3 distances, if we try to rank them, the D1 is closest to the theta 0. So D1 will have rank R1 equals 1. And the next one, in this case, based on what I draw, D3 appear to be closer to theta 0. So the D3 will have R3 equals 2. And for the D2, this observation over here, this is the most further D2 here, that's the furthest away from theta 0. Therefore, for that observation 2, it has a rank of 3. So that's how we rank the observations. And beyond the ranking, since we have the values either below the theta 0 or above theta 0, so we will also try to record the sign of this distance, whether it's on the right-hand side or on the left-hand side. If it's on the right-hand side, it's bigger. So simply if di is greater than 0, we make the sign to be 1. And if the di equals a negative value less than 0, we will make the si equals negative 1. So si is going to take values or for either a positive 1 or negative 1 if the di is positive or if di is negative. So basically that put all of those that are below theta 0. So imagine all the points below here, all of them si's are equal to negative 1. And all of those that are above theta 0 on the right-hand side, si becomes positive 1. Okay, So that's the sign. And the statistic in this case simply just take the signed rank and we sum up all of the possible signed rank. Imagine we have all those from the left side and also from the right hand side. These rankings, if really we have the median to be theta 0, in that case, these observations are supposed to be evenly spread out. And therefore, you can expect half of the points to the left-hand side, about half of the points on the right-hand side. So the signed rank of all those on the left side versus all those on the right-hand side would be roughly equal. So for that reason, this sum of the signed rank will be centered at 0. So that's if the null hypothesis. Under the null hypothesis, this W would be centered at 0, expected value of 0. And the variance in this case is related to the sample size. We're not going to try to derive that. Instead, we'll use this knowledge. This is the variance. And the distribution is also not a known distribution. Instead, it's a specific distribution. Once we know the distribution, then we will be able to use the distribution of W to compare, to decide whether the observed W calculated from sample is extreme or not. So for example, in the two-sided test, we would reject the null hypothesis if this absolute value of the test statistic W is greater than the critical value from the distribution of the W. As the sample size increases, this special distribution is no longer needed because that distribution is not easy to get. Instead, when the sample size n becomes large, the good part is the distribution of W will be approximately normal. And if that's the case, we can just use the W minus the mean 0 and divided by standard deviation as our test, as an approximated test statistic. And this one has a approximately normal distribution with mean 0 and variance of 1. So from normal, we can easily obtain the p-value and decide to reject null hypothesis or not. If p-value is less than the, like here, we use the normal, so normal distribution 0, 1, normal with mean 0, 1, for example, greater than this observed, let's call this one observed calculated value. This one is the p-value for the upper tilt test. This is the upper tilt test. And the p-value of lower tilt test would be corresponding less than the z. And for two-sided test would be the probability from the normal distribution with mean 0 and variance of 1 that is less than the absolute value of the observed z, and that's the two-sided test. Okay. As we know that in the Wilcoxon signed rank test, we expect that half of the observations to the left of theta 0 and half of the observations to the right of theta 0. Therefore, we could also use just those to the right-hand side, those ranks on the positive side, or use just those on the negative side. Either way, it would give us equivalent critical p-value. But of course, when you use just the positive ranks or the negative ranks, then the corresponding distribution will be also adjusted to its distribution. In the case that if we use the sum of these positive ranks, R has this P or the sign rank. This is the distribution in R sign rank. And if you will use P, it will give us probability of up to that value. And Q of sign rank will give us the quantile of this statistic. So that's for the positive sum of positive ranks. in addition to the situation that we have discussed here, we could also consider if the observations have some tight values. If that happens, the assumed continuity in the models would exclude those in the sense that the tie would not happen. But in practice, the measurement is always of a certain accuracy. For example, when we try to consider to measure the distance, we might have 1/8 of an inch, but we do not have arbitrarily smaller scales. For example, you might not have 10 to the -4, 10 to the -5. Therefore, if the measurement scale can only be precise or accurate up to 1/8 of an inch, in that case, the observed data might still have ties. Okay, so if data have ties, then what should we do? We are going to replace the ranking. Instead of ranks, now we're going to use mid-ranks. What do I mean by mid-ranks? Let's see, for example, suppose we have excuse me, I just accidentally touched, make it too far away, sorry, excuse me, let me go back. So for mid-ranks, what we're talking about is suppose the observed data are for example, we observed data 1.2, and then another data is 1.2, and then the next observed value is 2.1, and then 2.4, and so on. Let's say if these are the observed values, they are already ordered 1, 2, 3, 4. So if we are going to rank them, originally we would think that this is 1 and 2 and 3 and 4. 1 and 2 are actually for the same value, 1.2. Since they are for the same value, we're going to take the middle between the ranking of the two. So 1 and 2, we're going to use 1 and 2 divided by 2 for its rank. So in this case, it's going to give us 1.5 as the rank, and this one is also get 1.5 as the rank. And this one still gets 3, the other one still gets 4. So mid-rank basically means that when we try to consider the ranking, we will average all those if you have assigned just the rank. Okay, so that's about the mid-rank. So once the mid-ranks are computed and replaced the original rank, now we just compute the sum of signed rank. But if there is any of the observations that are tight, in that case, it will have 0 in the D. In that case, just discard the zeros and redo the ranking. Here's an example to illustrate. Suppose we are interested in the hypnotic susceptibility. We're considering whether a person before doing training and versus after training to see whether the training could actually increase the hypnotic susceptibility. So we have data that is observed for the same subject before training and after training. In this table, subject 1, before training, the score for the susceptibility is 10.5, and after training is 18.5. Similarly, for subject 2, we have the observed score of 19.45 for before training and 24.5 after training, and so on. We would like to see whether the training increased the hypnotic susceptibility. So to do the Wilcoxon signed rank test, we'll first compute the difference of all of those after training minus the before training. So this column DI give us the differences, and then afterward we would rank all these absolute value of the differences. As you see, with these values, the differences, we have a negative 1.5, even though it's a negative, but our ranking is going to be based on the absolute value. So this one will be a 1.5 rather than a negative value. Once we change it to 1.5, then this one is along with the 1.5, another 1.5, those two are together originally would receive a rank of 2 and 3, right? So here is rank 1, rank 2, and 3, but because the 2 and the 3, 2 and 3 are for the same value, both of them are the 1.5, so both of them will be converted to the 2.5 here. So that's the mid rank 2.5. And the others, like 3.5, becomes the next one, the ranking of the next one, which is the 4, and then the 5 and 6. So that's how do we do the mid rank. And then the sign here, the only one that has a negative sign is this negative 1.5. So we put a negative 1 here, and the rest of them have signs of positive 1. And when we try to consider the sum of rank, signed rank, we would use 6 times 1 plus 5 times 1 plus 4 times 1 and minus 2.5 and then plus 1.1 times 1 plus 2.5 times 1. That's the sum of the signed rank. And for the hypothesis here, we are looking at whether the after treatment it increased the susceptibility. So alternative hypothesis would be written as theta greater than 0. Null hypothesis is theta equal to 0. So for this case, when we try to do the test, this just basically listed the procedure I explained on the previous slide. So calculated the difference, calculated the rank and the sign, and get the sum of the signed rank. And once we get the sum of the signed rank, we'll try to use the distribution of the signed rank, sum of the Wilcoxon signed rank statistic to decide whether this is significant or not. We know the W is supposed to be centered at 0. In this case, we observed a value of 16 that basically says that it's big. But how big it is, that depends on how big is the variation. For this sample size, in this case particularly, we have a very small sample size of 5, but even with 5 here, the variance is 5 times 6 and times 2 times 5, 2 times 5 plus 1, and divided by 6. In the end, what we get is variance is 91. So if variance is 91, then the standard deviation is about 9.5. So if the standard deviation is over 9, in that case, observing 16, that's only about 1 standard deviation above the mean 0. So we don't really know whether this is just happened by chance or it's something that's really significant. So we'll try to use the probability to quantify that. This probability, in this case, we can use R to obtain the test p-value. You call Wilcox.test. So this is the test, Wilcox.test. And inside of that, you can feed the 2 samples, X and Y, and specify the alternative equal to quotation mark with the value, and specify whether the data is paired or not. And in our case, since we do have the before and the after training, so we are going to use X equals here the set of observations before training, and Y equals the set of observations after training. And afterward, we produce, we call this Wilcox.test. I'm putting in the Y minus X, but you could also do the Wilcox.test. And if you do the Y and the X, and then you specify alternative equals the greater, that will be the same. But in this case, you would like to specify that paired is equal to true. Okay, so if you do use the two variables y and x in the Wilcox command, the test command, you would like to specify the paired equals true. Okay. Once you submit that, you will get the test result, including the test statistic. For example, here the V is 18.5, that's the test statistic. And the p-value is also given. In this case, 0.05. For 0.05, we could always say that this is a marginally significant result. If you use 0.1 at significance level, then this is significant. If you use 0.05, then it's just at the cutoff, it's not significant. So that's the Wilcoxon signed rank test. The next part, we're going to consider the case that we are comparing two samples. You know, the Wilcoxon signed rank test in this previous part would handle the paired data. But if data are not paired, then we need to consider a procedure that allows to consider observations without being paired. We learned these parametric tests, for example, the two-sample t-test that include the large sample situation normal based on the normal distribution. That large sample case would require both sample sizes to be at least 30. And we also learned the case that the data that could be pulled if they have constant variance, and also the solution when they don't have constant variance, we have unpulled test. Either case, both of those actually, we're testing for the population mean, and we require either the distribution being normal or require the sample sizes are large. Again, practical data may not satisfy these assumptions, so what should we do? We will consider alternative methods to conduct the test. This Wilcoxon rank sum test is one alternative test that can be used to do the two sample comparisons. For the Wilcoxon rank sum test, this basically is trying to consider all possible scenarios of ranking the observed values from these two samples, and then consider simply just sum of the ranks in one of the sample, and then try to see whether that sum of the ranks is too extreme or not. Let's say, suppose we have data observed that's denote them as x1 through xm, that's from the one sample. And for the other sample, that's denote them as the y1 through the yn. And what we wanted to do is to put the combine the samples together and rank them. So here we have total of m plus n observations, and then when we try to rank them, we will have ranks for each of the observation. And now some of them are for the observations in the first sample. Let's denote them as R1 through Rm. And the ranks for the second sample, let's denote them as S1 through Sn. And for these rankings, if there are ties in the observations, also use the mid rank. Okay. So basically, we have all those rankings or mid ranks. The next one is to put the statistic as the sum of the ranks in one sample. This one, here this Wx is the sum of ranks from the first sample, and Wy is the sum of ranks from the second sample. Imagine all these rankings. Since we combined the two samples together, there are a total of capital N observations, where this capital N would be the total number of samples from both samples. And therefore, when we finish ranking, what we are going to have is these observations will have one of them being the smallest, receive ranking of 1, and the next one will receive rank of 2, and so on. And the last one receive the rank of capital N. This is if there's no ties. If there is a tie, for example, first and second observations are tied, in that case, these two will be simply averaged rather than the 1 and 2 will be averaged. But when you average 1 and 2, that's the same as you still have the 1 and the 2. Therefore, when we consider the total ranking, the sum is still just from 1 up to n being added up together. And this is the overall ranking, the sum of the ranks from both samples. So that the sum of ranks is fixed. If that's the case, we consider the sum of rank from the x, like this one. If we have this value computed, then we know what's the sum of rank in the other sample because the total is fixed value. So whether we consider to use one of them or we use the other, that does not make any difference. These two sum of ranks procedure would be equivalent. Let's illustrate this Wilcoxon rank sum test with this real data. Suppose here we're considering a new method for teaching new employees, to see whether the new method is better than the traditional method, in the sense that after they train these employees, teach their employees with the new method, they might achieve a higher score. So for the new method, the observed scores are 37, 49, 55, and 57. And traditional method, the scores received are 23, 31, and 46. These are all the observations that we have. Obviously, it's a very small sample size. Because of the smaller sample size, and we are not able to check whether normality assumption is reasonable or not, in this case, let's directly consider the rank procedure, Wilcoxon rank sum test. So to rank the observations, we will first consider listing all the observations together. So in this case, here are the observations from the new method, and these are the observations from the traditional method. We're pulling them together to consider the ranking. So out of combined the total of 7 observations, the smallest one is 23. So that receives the rank of 1. The next smallest is 31, that receives the rank of 2. And the third smallest is 37, it receives the ranking of 3, and so on. Continue. So that's the ranking. And when we consider the test statistic, we can sum all of the ranks from one sample. For example, if we simply take the sum of the ranks from the first sample, from the new method, in that case, we will be summing up these values, 3, 5, 6, and 7. And that will give us the sum of ranks from the new method being 21. If we use this one, we would first need to figure out what is the possible other sum of ranks for those in the first sample in that new method. Okay, to do so, let's consider to list them together. Before we'll talk about the hypothesis later. Okay. So talking about the sum of ranks, actually the sum of ranks will depend on how the hypothesis is specified. In fact, in the parametric method, we always specify the hypothesis in terms of population parameters, such as the mean being equal. In this case, we are actually working with the distribution. So the null hypothesis, in fact, is to specify the distributions are identical. Because if you try to rank the observations together, you really think that these observations can directly be compared to each other. So the null hypothesis is specifying that the distributions are identical. So this is the CDF of the two distributions. We specify the CDF of first one, F1, to be equal to the CDF of the second one. So that's the null hypothesis. And when we are interested in the lower tailed test, we would specify the research hypothesis as F1 to be less than equal to F2. What does this mean? The CDF, we know, is always a non-decreasing. So basically it goes up, always kind of go up from the 0 all the way to 1. So what I mean 0 is if you consider here's the vertical axis, that would be the 0, there is the 1. CDF is always increasing. And now we're considering two of the CDFs. One is that red one, and the other CDF is this blue one. And when we are looking at F1 less equal to F2, for example, here is for this X value, and this is the F1 X, and this is the F2 X. The F1 less equal to F2, that really means that probability of this F1 is for X, okay. So F1X is equal to the X that's equal to X. On the other hand, the F2X is the other sample, Y that's equal to the same little X. If F1 is lower, that means there are, okay, F1 is lower, less values of F1 is smaller, is on the left of X, right? So if F1 is less equal to F2, that means less values of F1 is to the left of X. Therefore, if you see how many of the values are to the right of that, generally that would say that F2's value tend to be, that observed value tend to be bigger. So in the distributional, this kind of hypothesis written in terms of the CDF, F1X less equal to Fx, F2X, that means there are less of the observations in the F1 that are smaller. Okay. So that's lower tailed hypothesis. And the upper tailed research hypothesis is F1 greater equal to F2. If F1 is greater equal to F2, that means more of the X values are smaller. Okay. So that's one-sided hypothesis. Two-sided hypothesis, in this case, we are looking at F1 less equal to or F1 greater equal to F2. So that's the two-sided hypothesis. And in some cases, we might be able to specify the hypothesis in terms of population parameters. If you do so, you are making assumptions. For example, you might want to specify the null hypothesis in terms of the mean. Mu1 minus mu2 is equal to 0, and the research hypothesis is specifying mu1 minus mu2 greater than 0. If you are making this assumption, you are really assuming this actually is making more assumption. This is assuming that the distribution F1 and F2 is identical. Identical under the null hypothesis, assuming, okay, this is making an assumption of assuming here, but it's not testing, but making an assumption. So if the null hypothesis is not true, if the alternate hypothesis is true, then it's assuming that the F1 of X minus this difference, mu1 minus mu2, and the F2 of X are identical. Okay, identical. So as you see, if you are trying to write the hypothesis in terms of population parameters mu1 and mu2, then you are making additional assumptions. And if the hypothesis is rejected, you really do not know it's because the assumption is wrong or because your hypothesis is not really supported. So here, this part, just keep in mind, the real hypothesis should be in terms of the population CDF rather than in terms of the parameters. If you're forced to test about population parameters, that require additional assumptions in there. Okay, so this is basically considering how do we perform the test. First, combine all of the observations into one group and rank them from the smallest to the largest and assign the ranks. These ranks, after we assigned, we will only sum up the ranks in one group. For example, only take the sum of the ranks in the group 1, and then find all possible ways of assigning the ranks to these observations in that first group. And say we have m observations in the first group and n observations in the second group. We would consider all possible ways of assigning the ranks into these total of m plus n of them. This one is not considering any hypothesis or considering any data, just all possible scenarios. I will illustrate that soon in an example, okay? And we call these all possible ways of assigning the ranks as a permutation of the ranks. So this is talking about the permutation of the ranks. It will soon be clarified on the next couple of slides. Once we have all these possible ranks considered, then we sum the ranks for the group 1. So there will be many different of those for the group 1. And then we'll try to consider the number of the sum of the ranks in group 1 that are less equal to the observed calculated sum of the rank from the data. This is the only part that relies on the data. And this part comes from the all possible scenarios. And this is for the upper tailed test. Recall, because upper tailed test is talking about F1 greater than F2. And F1 greater means that there are more observations than on the left side. Therefore, we look at less equal to. This is the critical thing. For the lower tailed test, we will look at out of all those possible assigned ranks, the number of the sum ranks greater or equal to the observed one, and then divided by the total number of ways of assigning the ranks. In this case, the total number of ways that we could assign the ranks is really the combination number of m plus n choose n. That's illustrated with an example. In this example, let's see how are these rankings done. Okay, we have a researcher interested in comparing men and women to see whether men download more movies onto their computer than women. And we have the data from 3 men and the data from 3 women. And here the data is how many gigabytes of movies they had on their primary computer. So for men here, 305, 16, and 122. And for women, the observed values are 25, 85, and 103. So based on these observed values, we want to test whether men tend to download more movies onto their computer. So men download more movies. Okay, F of men more movies. If there are more movies, then that'll be less than okay, I'm sorry, it's the other way. Yes, the men download the more movies. If men download more movies than the female, and okay, when they download the more movies, in the CDF, more is on the left side. Therefore, this one is for men, and then the women would be the other one. This would be the women. So, I'm sorry. Yeah, I'm sorry, that was not correct. So if men download more movies, men's values are larger. So here, these are the X values. Men's value are larger. Larger means that more on the right-hand side. And women, on the other hand, would tend to be smaller. So for the women, their observed values tend to be on the left-hand side, which make the CDF to be bigger. Okay, women would be bigger. Why? Okay, so that's the women. And if it's higher, like for example, up to here, more on the lower side, because more of those less equal to X, that means more of the values are on the left-hand side. So for CDF, when we say men download more movies, we would look at the CDF of men less equal to CDF of women. Okay, this is the research hypothesis. We want to check whether there is evidence to support this research hypothesis. And for this one, when we try to consider the ranking of all possible scenarios without looking at our data, since we have, let's say, go back there. How many observations? 3 here, 3 there. So total of 6 observations. Therefore, if we consider all possible rankings, you could have the first is for men, okay. You could have all the men's rankings are the smallest, therefore the smaller ones, so you see the 1, 2, 3 as the rank. You could also have like the 3 being from the women. So you have 1 to 4, for example, and 1 to 5, 1 to 6, and so on. So basically, out of 6 possible values, 1, 2, 3, 4, 5, 6, we're going to pick 3 of them and use it as the rank for the men. These are we are looking at all possible scenarios. All possible scenarios. All possible situations of ranking. Assign ranks. So for these all possible situations of assigning ranks, we have 6 of them. We are really just picking 3 of them, put it on the men's side, and leave the remaining 3 for the women's side. Like this one is picking 1, 2, 3 to assign it to the men's value. Remember, okay, these are the all possible scenarios without looking at the data. Why do we have these all possible scenarios? Because if the null hypothesis, if the null hypothesis is true, in that case, men and women, they have the same distribution in terms of the observed values. Therefore, if the same distribution, then these observations, whether it come from men or come from women, they should be equally likely to be anywhere when you consider these 6 observations. There's no reason for the men's values to be larger or smaller. So if men and women's observed values to be equally likely to be among these from 1 to 6, then we could just assign any of the 3 to the men. Okay, that's why you see all these possible ones being listed as the possible assigned rankings for men. So how many of those? This is choosing the 6 values, choosing 3 out of the 6 values. That's the 6 choose 3, which is the number of ways of computing that is really like the 6, 5, and 4 times together divided by the 3, 2, and 1. And in the end, what you get is the 20. That's why you see 20 of these listed scenarios. For each one of them, let's compute the sum of ranks. 1 to 3, you get sum of rank 6. 1 to 4, sum of rank 7, and so on. So that's all possible ways of assigning the rankings and put 3 of them given to the men. And the next one is to look at the rank in the observed data. For the observed data, we only have these 6 numbers, and the rank would be straightforward. For example, here 16 is the smallest, it receives rank 1. 25 is the second smallest, it receives rank 2, and so on. When we consider the test statistic, we'll sum up the ranks in one group, like the men. For men, summing up the rank 615 will add up together, that give us the 12. And next, we'll try to look at this 12 compared to all those in the table that we listed, our possible scenarios. How many of them are bigger than 12? Because 12 is the observed. So how many are bigger than the 12? Those are the extreme case. Bigger or equal to the 12. That's one, that's another one, and these. All these greater or equal to 12 are the ones more extreme than the observed 12. So how big is this probability? In this case, we have 7 of those greater or equal to 12. So this probability of observing more extreme than those in the data is really 7 out of the 20. And therefore, this probability is 7 out of 20. That is 35% of the chance, there's a 35% of chance that the possible sum of ranks from men could be greater than or equal to 12 if the null hypothesis is still correct. So with 0.35 as the probability, then we know that this is not a very small chance. So it could happen simply just by chance. Therefore, with that, we would say that there's no evidence to support that men download more movies than women. Okay, so by looking at these numbers, we tend to say that men may be downloading more, but because of the variation is really big, in this case, we cannot rule out simply just by chance that these numbers happen to be bigger. Okay, that's the Wilcoxon rank sum test based on the permutation to obtain the p-value. Permutation is listing all possible scenarios. In the previous example, we see with just 3 observations in each of the sample, it already has 20 possible scenarios. Now, if you increase the number of samples, then the number of permutations will become too large to consider all possible ways. So if the sample size becomes larger, particularly if 8 or more, then it's just not possible to consider all possible permutations anymore. In this case, what we can do is to use a normal approximation for the distribution of the test statistic. In this case, if we consider the sum of ranks in the X sample, then the sum of ranks minus the mean divided by standard deviation will be approximately normal with mean 0, variance of 1. And this mean of the rank is equal to the 1/2 times m and n plus 1. Why is that? Because if all of the observations are equally likely and they are all possibly receiving either 1 or 2 or n plus 1 as the rank, and all of them equally likely, the probability, then the mean of that is really, the mean of these rankings is really the middle. And this middle here is n plus 1. I'm sorry. Here we were talking about from 1 to n are the possible rankings. And then when we try to consider the middle, that'll be n plus 1/2. That's the middle part, the middle here, okay? And for one of them, the average rank is n plus 1/2, and there are m observations there in the first sample. So the sum of ranks in the first sample would be half of the m times n plus 1. And the variance here in this case is equal to the m and n times n plus 1/12. Again, it's also because of 1 to n, each one of them is equally likely. This is the discrete uniform distribution's variance. So that's the mean. If you consider the sum of the ranks in the Y sample, in that case is similar, we simply just change the mean. The mean for the sum of ranks in the Y sample is the number of samples n here times the average n plus 1 over 2. And variance is identical. So in either case, you use the sum of ranks minus the mean average, sum of the rank, the mean, divided by the standard deviation. That's approximately normal. And then we can use the normal distribution to figure out the p-value. Okay, this next part is considering what if there are ties. This first point is here was just trying to say that the distribution of the Wx is symmetric. If it's symmetric, then the left tail probability and the right tail probability is the same. So that part is rarely used, so we don't have to worry too much about that. Instead, let's consider what if there are tied observations. If there are tied observations, the mean would still maintain to be the same, but because of the ties, variance of these sum of ranks will change. This variance now need to consider how many of them are of identical ranks. So suppose, for example, in one group there are 3 tied ranks. Then this T1 is counting how many of them are identical. So T1 equals 3. Consider the different groups of tied values. We simply use this T sub j to record how many of them are identical value. And this variance would need to be adjusted based on this number of tied values. This part. Let's see for an example. In this example, we're trying to consider the food safety. Those in fairs and festivals, we want to see whether the food cooked at these, for example, the food trucks, whether people who buy the food from there, whether they think it's safe or not. Here, let's consider we have data collected, and the responses possible are 1 means a person thinks that it very rarely will make people sick, and 2 would be the person think that it's once in a while it could make people think, and 3 means often make people think. This is what people perceive, people's response about how they think the food prepared at these outdoor fairs and festivals, how safe they are. So that's the possible values recording from the participants, and then let's see, here are the data. And what is in the data here? 13 means that there are 13 females who says that who give the response value of 1, and 108 are those females that give a response value of 2, and so on. So in this case, what we observed is really that we have 1. So the values are really 1 and continue, and you repeat this 13 times. So out of that, there are 13 of those these are the female. And similarly for male, there are 22 of them that recorded the value of 1. So 22 of them are for male, and so on. And then the 108 female and 57 male, and so on. So these are the actual observed value. And then when we try to conduct the test, we will need to use these values 1, 1, 1, 1, and so on, and then run the Wilcoxon rank sum test. So when we do that, these tied values will receive mid-rank. For example, let's consider response value of 1, 1 here, okay. There are a total of 13 plus 22 equals 35. That many responses are 1. So if we consider the mid rank, they are really 1, 2, up to the 35, and all of them are added together and divided by the 35. So that gives us the 18 as the mid-rank of all the responses that give value of 1. And then for the 2, how many give response value of 2? That's 108 female, 57 male, total 165 of them. And this many, 165 of them, originally we already have 35 of those receiving the first response. The next now would be originally receiving the rank of 36, 37, and all the way until this 36 plus 165. This is the last one in terms of the ranking, and this is for 165 persons. That gives us a total of 118, average of 118 as the mid-rank for response value of 2, and so on. So those are the mid-ranks. And next, let's consider what are the T sub j's. This count 35 here, this is the T1, and this is the T2 is 165. And there is the T3, which is the 72. And here's the T4, and there's the T5. So these are the number of people that have the tied responses in each subgroup. And when we consider the variance, we'll have these T sub j minus 1 and T sub j and T sub j plus 1 in the calculation. Okay, so that's the variance part, and the mean part, we are looking at how many that receive the mid-rank 18, how many receive the second mid-rank, and so on. This is the sum of ranks in the one group. So if we go back, 22, this is the males group, okay? For a male group, we have this as the average rank, and then variance is this much. And then when we try to consider the test statistic, we'll use the sum of rank here minus the mean and divide by square root of the variance. And that gives us the statistic. In this case, we get the value of negative 3.3 something. And for a two-sided test, if it's two-sided test, we'll use twice of the standard normal that is less than this value, because for normal distribution, standard normal, here is negative 3.3 here. And it's two-sided. We're looking at both the right tail and left tail. Twice of p-norm, and with this value, that gives us the p-value. And this computed p-value is about the 0.000856. So this is if we do the calculation based on this normal distribution. And this value is apparently significant if we use 0.05 or 0.01 as significance level. So if it's significant, then we believe that the men and the women, they do not have the same level of concern in terms of the food safety. So for this example, you might be attempted to directly use the t-test to do the test. If you do so, the t-test will give a test statistic 3.3, and p-value is also pretty close. But the problem with that is using the t-test, you are really thinking that the observed value of 1 through 5 are really meaningful numerical values. But if we really go back to think, what are those values 1 through 5? 1 is talking about very rarely, and 2 is once in a while. So if we have value 1 and 2, we know the distance is 1, and value 2 and 3, the distance is also 1. If it's a numerical value, that distance is really meaningful. But now, if you look at very rarely versus once in a while, that distance you call it 1, and this once in a while versus often is that distance also 1. This distance in the case when we have this kind of categorical responses, the distance does not really make sense. It's not really meaningful to have such distance. So if you treat these values as 1 to 5 numerically, it's really inconsistent with the meaning of these categories. Therefore, if you use the t-test, you are assuming 1 to 5 are meaningful in terms of even computing the distance. The rank tests do not have such assumptions. Just believe that those categories like rarely, once in a while, and so on, they are ordered. And as long as they are ordered, we can rank them. So this is better to use the Wilcoxon rank sum test than the t-test. Okay, another thing I did not put onto the note is that the Wilcoxon rank sum test, if the normal assumptions still hold, in that case, the Wilcoxon rank sum test has efficiency like no less than 95% compared to the t-test. On the other hand, if the normal distribution does not hold, in that case, the Wilcoxon rank sum test would have much higher efficiency compared to the two-sample t-test. So regardless of what situation, in fact, the Wilcoxon rank sum test is recommended to replace the two-sample t-test. How do we conduct the Wilcoxon rank sum test in R? We can simply just use this Wilcox.test and specify the men and women. But in this case, this is the identical command like the assigned rank test, except now we do provide the two variables, the men and the women. And in addition, we no longer specified the paired, right? Previously, the paired in the example, when it's paired data, we need to specify paired equals true. And here, when we don't specify, the paired is default to use paired equals false. So that means we are dealing with two samples that are not paired. And in this case, alternative, if we specify as greater, in that case, we'll get a p-value of 0.35. Recall, for this one, we did the two-sided test. When we did the two-sided test, we could not get significant results. Similarly here, even with one-sided test, our p-value was 0.35. 7 out of 20, yeah, that was the same. The result is not significant. So in this case, we have pretty easy to compute our command to conduct the Wilcox test, Wilcox rank sum test. A little bit difference of this hypothesis listed here is that this is talking about the location shift instead of in terms of the distribution. As I explained earlier, the distribution was the inherent distribution is the inherent hypothesis in terms of distribution. But in this one, the R implementation, it really did not put the distribution in there. It was putting the shift in there. So if it is putting a shift there, there is an assumption. This assumption is like the two have identical distribution, except that they have one little shift there. In other words, if you consider this one as a CDF and the other one is also a CDF, the red one, and this red one, you just need to shift it a little bit to make it equal to the other one. Okay, so that's in terms of the two distributions. And once you specify this one as an assumption, and this assumption is regardless of you like it or not, this is built in there as assumption, and this assumption might be wrong. And then once making that assumption, the hypothesis now is specified in terms of the shift being 0 versus the shift is greater than 0 or less than 0 or equal to 0. So that's the Wilcoxon rank sum test if you want to specify hypothesis in terms of the shift. So what will happen in this case if do not reject, if you fail to reject the null hypothesis, okay, fail to reject the null hypothesis, then you can conclude no evidence to support this delta not equal to 0. No evidence for that. But if you reject the null hypothesis, reject it null, then we don't know. We don't know if it's because the shift is not 0 or the F1 not equal to this F2 x minus delta, because that assumption is also part of this procedure. So if you reject it, then you cannot really conclude that the shift is not equal to 0. So if we reject null hypothesis, we can only say that the two CDFs are different. We cannot really say that the shift is not equal to 0. This one is for the safety if we want to perform the rank sum test, because what we observed are those tabulated count of value of 1, 2, 3, 4, and so on. So we really need to recover the original count, the original response. In this case, the men, we observed 22 of the ones, 57 of the twos, and so on. And how many for women? 35 of ones and 165 of the twos, and so on. I'm sorry, the 35, 165, and so on. That's the total of the count for 1, 2, 3, 4, and so on. And therefore, for women, how many times are observed for 1? That's 35 minus 22. And for men, for 2 would be 165 minus 57. So if we simply just take the difference, that's the total repeat minus men's repeat, we get women's repeat. And then when we try to record the original observed count, we simply just use this replication command, REP. And what are the values from 1 to 5? And each of these values, 1 is repeated how many times? That's men's repeated the first entry. This one, 1 is repeated, so repeat 1 22 times. And 2 is repeated 57 times, and so on. Similarly, for the women here, 1 is repeated 35 times, and 2 is repeated 165 times, and so on. So once we do that, then you can check the DAT men would contain 1 22 times and 2 57 times, and so on. Now you're ready to do the Wilcox test on the data. So you put the DAT men and DAT women in there, alternative specify two-sided, and we'll get our statistic and the p-value. So for this case, our p-value is 0.008575. So with that p-value very small, even though it tells you that the alternative hypothesis says shift is not equal to 0, but we really cannot really tell whether it's because the shift is not equal to 0 or because the assumption that the CDF, on previous slide, we mentioned that whether it's because of this part being violated or this part being violated, we don't really know. Okay. So that's the two-sample comparison. We use Wilcoxon rank sum test. So both previous tool, Wilcoxon signed rank test and the Wilcoxon rank sum test, both of them are conducted in R with the same command, wilcox.test. The next part is the Kruskal Wallis test.